Good afternoon, ladies and gentlemen. My name is Dr. Jon Belkowitz. I'm the director of R&D at Intelligent Concrete, where we specialize in making concrete do the impossible. Today, we get to explore what we like to call the magical world of concrete, specifically answering a question from one of my favorite YouTube personalities, the Swedish Death Llama. Pew, pew, pew! Wait, is this from Swedish Death Llama?
Yeah.
Oh, cool. Swedish Death Llama. Can you do the pew, pew, pew?
Pew, pew, pew.
Yeah, you know what? You're talking to Brooke, and I don't feel like you're doing the pew, pew, pew with all the emphasis that you had intended. Now it seems like you're rushing the pew, pew, pew.
Pew, pew, pew.
All right, so
Okay.
tangent. We've got an awesome question. Ding! From Swedish Death Llama. The question goes, what would you do to make concrete survive 800C, 1500F temps from jets, vertical takeoff and landing? I can answer this question. I didn't really read the whole question. I can't answer it all the way because we are working with certain government agencies on this type of concrete. But I'll answer it in the most vague way I possibly can. I think I even have a presentation that I put together on this subject, answering it a very vague way. Okay, hey, so we're going to be switching over to this presentation. I'm going to do a voiceover.
Pew, pew, pew. Pew, pew, pew.
So much better. Okay, so we're starting at, the purpose of what we were doing is designing this either blast absorbing grout. I was talking to a grouting committee, or blast absorbing concrete. And the innovation density or definition is that we want to change up the density of these materials while keeping our high strength and our placement methods to go after this different type of material. Concrete is not designed to absorb blast loads and stay together. We do this because we want to create a concrete that has certain security measures, not only for buildings that are in place with definite security parameters, but hardening shelters that at one time might not have needed blast absorbing protection, and then of course civilian and force protection if it's only a semi-permanent status. When we look at blast absorbing concrete, there's three things that we want to focus on. The first one is energy absorption, second is compressive strength, and third is anti-shrapnel. And that's the thing, a blast load can do one of two things to concrete. It normally does both, and it's the combination of the two. It either can move concrete or it can destroy concrete. And it does a combination of the two, and we call that shrapnel. So we want to create a concrete that when it does get blown up, it doesn't create that shrapnel. Alright, so energy absorbing, what we want to focus on is that blast energy wave if we're looking at blast loads. And we want to move or change that grout structure so that when the grout structure feels the application of that blast load, instead of the total concrete composite or the total element picking up and moving, the structure fails within itself. So the grout structure moves and it destroys itself to absorb that blast load. And eventually, we can't predict all blast loads. The way it was explained to me by one of my mentors, we don't talk about pounds of C4, we talk about Greyhound buses. So it's the size and the number, or it's the amount of people in the Greyhound bus and the number of Greyhound buses with or without people that we're throwing at this concrete structure, not the pounds of C4. And that's the type of blast loads that we look at. And what we want to really understand is that we are not going to predict what that enemy blast load size is. So we kind of have to understand at a certain point we are going to turn that concrete into rubble and shrapnel if the blast load is big enough. Now if we're looking for bullets, we want to collect those bullets. We want to absorb them. We want to catch them. Many years ago when we first started designing blast absorbing concrete for a government entity, we started out by making these bullet catching business cards. And this was the alpha model for that blast, and I think we did a video on this, right, Haley? So yeah, we created these bullet catching business cards, and that's one thing that we want to do with this technology is create a structure that again destroys or falls on itself when we get that bullet mini blast load, if you will, and then instead of it becoming shrapnel, either the bullet bouncing off the concrete or the bullet hitting the concrete and destroying it and making things fly out, it gets absorbed. It destroys the concrete and it gets absorbed into it. Now, the hardest part of this is how do we do that while still maintaining those compressive strengths to design structures. And one of the biggest ways of creating a lightweight concrete that can collapse in on itself was using something called a cellular concept, where we're taking that air and training agent that we use for freestyle durability and we're bastardizing it like a champ. We're using it instead of 5% air, we're creating 10, 20, 30% air, and that lightness, that change in porosity, that change in pore connectivity gives us that hydrated cement matrix that's going to collapse on itself. The problem with that is the amount of air that you have to add. The unfortunate reality is you're going to create concretes with strength that are below 1,000 psi. Concretes that you really can't use for structural elements unless you're starting to make a really big wall. Instead of an 8-inch wall, you're making a 2-foot or 3-foot thick wall. So in lieu of doing that, what we can do is, instead of using this injected air, we can use engineered cavities from lightweight expanded shale, soda lime borosilicate, expanded rubbers or polymers, something that has a structural network to it as well as a hollow cavity, so that it can offer some good strengths as well as that lightweight characteristic, as well as that characteristic of destroying itself as it absorbs that blast load of that bullet. Next slide. So other cavities that you can use, polystyrenes, whether extruded, they're made out of what's it called, 3-pound or lower density polystyrene foam, the beads. You can use geomess, fiber messes, anything that creates an engineered cavity, which is more than messing with the mix. Now you're engineering the composite. Compressive strength, this is the dance that you have to take. If you start making your concrete too soft, yes, you're going to get something that absorbs blast loads, absorbs bullets, but it's not going to be strong enough to create a structure out of it. So using something outside of that cellular, that air concept, using those expanded shales, soda lime borosilicates, rubbers, polystyrenes, polyesters, even plastics, can get you to that same place without sacrificing that strength. And what we want to do is optimize our hydrated cement matrix to get it as strong as possible, as tough as possible, as durable as possible, and then sacrifice some of the granular skeleton that we're using with the other materials that we mentioned in lieu of using the more traditional aggregates. But again, it's optimizing that hydrated cement matrix so we can start using that lightweight aggregate for these blast absorbing methods. Going into anti-shrapnel. With this, we want to create not only a composite that is softer, that can fall in on itself with that different type of loading, whether it's bullet or blast load, but also we want to create something that when it does crack, when it does destroy on itself, it doesn't start flying apart in pieces. And to do that, we need to use things like fibers, polyester fibers, polyvinyl fibers, as well as things that are fibers but act more on a molecular level, because once we deal with that, so we want to put something in the mix in the hydrated cement matrix that's going to hold everything together. So not only those fibers, but we can also use carbon nanotubes, carbon nanofibers. There are certain polymers that we can use that hold the concrete together. It needs to be more of an elastic glue instead of a ceramic glue, so that when we do see that deformation that would cause that catastrophic failure of the hydrated cement matrix, this stuff takes over and holds that hydrated cement matrix together. We did a wonderful experiment today where I had our wonderful intern Joe Dabucci take a beam, right, Joe? And I said, let's run the experiment. We're going to throw it on the floor. And what was the beam? 1 inch by 1 inch by 11 inches. And what do you think is going to happen? And what did you think was going to happen?
It's going to, break.
Crack. Catastrophically crack.
Yeah.
It's not plastic. It's not steel. It was a mortar.
Yeah, brittle.
Now, what would happen if you remember that Flex Seal commercial? You can take a screen door and put it on the bottom of the boat, spray it with Flex Seal, and you have a boat, right? So if we sprayed that stuff on top of concrete and ran the same experiment, what do you think would happen?
We'll hold it all together.
Hold it, still break though.
Yeah, still break.
But it would hold it all together. That's one of the things that we're looking for in this anti-shrapnel, is even after the bullets or the blast load destroys it, it still holds the concrete. Now, you can go after the cheap concept or the cheating concept of spraying the concrete from the outside, but the cool thing is design something within the hydrated cement matrix that does the same job. So I have a lovely photo here of some carbon nanotubes. We can't use that photo. That doesn't belong to us. Sorry. It's a great photo. I'm sorry you can't see it though. It's such a shame. Yeah, you guys should come and see it. No, it's really like a wow, wonderful photo. Yeah, so what you see here, sorry for the folks at home, you gotta keep this in here, like this portion.
Yeah.
But, so what you see here is the carbon nanotubes. Now these carbon nanotubes, remember, it's a fiber that has been functionalized in a way that the hydrated cement grows into it, and not only is there a mechanical bond between the asperities of the hydrated cement matrix, those microscopic mountains in the carbon nanotube, but there's also a molecular bond, assuming that it's functionalized, so really anchoring it into the hydrated cement matrix. So if this piece gets broken off and it wants to explode out or wants to tear out, instead of tearing out, it's going to be anchored in place by the carbon nanotube that is anchored into the adjacent concrete. Does that make sense?
Mechanically and chemically.
Boom. So yeah, sorry you can't see this picture. It's a pretty dope picture. Like, that's
cool.
nice.
It's very cool.
Such a shame. Sorry. Let's blame it on who are we blaming it on?
Haley.
Let's blame it on Haley. Definitely a Haley fault there. No, it's not. That was my fault. I apologize profusely, but you can't see it. Now, emerging technologies, you could definitely leave this one in, Haley, not the picture, but the list. But in this, I talk about emerging technologies. I talk about fibers, that weird polyvinyl, polypropylene, big fibers that we can see. Carbon nanotubes, carbon nanofibers, multi-wall carbon nanotubes. I even talk about Kevlar, fiberglass, steel, mesh, and then I mentioned something called gooey fibers. That sounds fun. We had worked years ago for a client that had this idea of making a fiber that was gooey. Not gooey in the sense of that it didn't hold its own shape, almost gooey like a gummy bear. Or you remember those toys you had as a kid that you threw like this stretchy thing on the wall and it stuck and it got all dirty and nasty like within like 10 minutes of using it? That was the same concept, but our client was using an inorganic polymer to do the same thing, and these gooey fibers, they stretched, they had an elongation that was either 10 or 15 times its original size, but then once it reached that capacity, it had a tensile strength that was, greater than either rubber or whatever it was that had the same stretching ability, so that you could have that catastrophic failure, you could have that release of energy, but it wouldn't allow that shrapnel to go and do harm. It actually still would be connected to the concrete. So using a lot of these technologies in combination, next slide, you can recreate that vision of a blast absorbing, I put grout here, but it's really a cementitious composite, whether it's grout, concrete, mortar, or even a neat cement paste. So, yeah. So thanks for joining us. Hopefully you learned something today. So getting back to Swedish Death Llama's question, what would you do to make concrete to survive temps 800C from what is this, Vital?
VTOLs, I don't know.
What's that?
VTOL.
A VTOL jet.
A jet, a vertical takeoff and landing. So that's the first thing. That's blast absorbing. That you want to create something that's tough and durable, that it can absorb the load and then not destroy from there. But then there is the heat component of it. And with things like heat, you've got to use denser materials. So you're combining a lot of things that are really contrasting. What I would recommend for this, I'm going to take a different approach. This is not just blast absorbing. What I would do with this is I would go in the opposite direction that I just talked about. I would go with the combination in heat and of the blast loads that you need and the abrasive wear that you're getting from the aircraft. I would go with an ultra high dense concrete. Use something like a hematite sand. Take all your air out of it. Use a defoaming agent. Your binder, your hydrated cement matrix. I would do something around, well, Swedish Death Llama, so he's in Europe, so he's using kilograms per cubic meter. I would use somewhere over 400 kilograms per cubic meter. I would do a combination of silica fume, metakaolin, somewhere between a 5 and 10% combination. And then I would throw some colloidal silica in there, somewhere around a 10 to 12 nanometer at around 240 milliliters per 100 kilograms of cementitious material. I would use a high-range water reducer to drive your water cementitious ratio down. Again, yeah, I'm going the opposite direction with this. I'm making one hell of a dense concrete. Think of it as creating, there's a great paper by Brian H. Greene from the U.S. Army Corps of Engineers, which was published in the late 90s or early 2000s. It's on a rock matching grout that was used for nuclear payload testing. Swedish Death Llama, read that paper.
Link below. Ding!
There's your answer. Thanks for joining us today. One hell of a question, Swedish Death Llama. Go concrete!
Beat asphalt!